So as we're finishing up our notes from this section, let's go over mixture problems. In these problems, imagine that we have a tank and we have some kind of solute or chemical, something that's coming into the tank at a given rate. And then we also have, after we have supposedly perfect mixing within the tank, an amount of the tank coming out. Our goal in these problems is to find an equation that represents x of t, which is the amount of the solute in the tank at time t. So we're not looking at how much liquid is in the tank at time t. We're looking at how much of the material that's coming into the tank remains in the tank at time t after we've been mixing the tank, and also some mixture has been leaving the tank at a certain rate. Now this x of t is going to be difficult to describe directly. However, the rate of change of x with respect to t is a bit simpler to determine and figure out, and then from that, if we can solve this differential equation, we will be able to isolate x of t. So in these problems, the rate of change in the amount of solute in the tank at time t can be described by the rate in times the pollutant concentration in, or whatever the solute is, minus the rate out times the concentration of what is coming out. Now generally, we will be told clearly what's coming in, we'll know the rate in, we'll know the rate out. To find the pollutant concentration that's coming out, that's always going to be the amount that's in the tank divided by the volume of the tank at time t. And we calculate the volume of the tank based on what our initial is and how the materials are going in and out of the tank. So let's look at our first example. Suppose a water tank is being pumped out at 3 liters per minute. The water tank starts at 10 liters of clean water. Water with a toxic substance is flowing into the tank at 2 liters per minute, and the concentration of the toxic substance is 20 t gallons per minute at time t, grams per minute, grams per liter at time t. When the tank is half empty, how many grams of toxic substance are in the tank, assuming perfect mixing? So quickly, through reading the problem, we can gather a few pieces of information. We know that water's flowing into the tank at 2 liters per minute. It's being pumped out at 3 liters per minute. A key thing that we'll keep in mind for later is we care about when the tank is half empty, what's the amount remaining in the tank? Now we started with 10 liters, so when the tank is half empty, that's when our volume equals 5 liters. So we'll just write that down, that will come into play later. So we know our general rate of change of the amount of the solute in the tank at time t can be given by the rate in times the pollutant concentration in minus the rate out times the pollutant concentration out. So for our particular problem, the rate in is 2 liters per minute. We were told our concentration is 20 t. Our rate out we know is 3. And then our pollutant concentration, we know that's going to be the amount at time t, which we will just say is our x, divided by the volume. Now let's figure out what the volume would be at time t. We know our initial volume was 10 liters. But we had, in addition to this 10 liter initial, we have stuff coming in and going out. So it's particularly our volume at time t, for t is in minutes, is our initial 10 plus, now this is our change. We have 2 going in for every 3 going out. So our net change is we're losing 1 liter per minute. So that's why the way the volume changes in the tank with respect to time is 10 minus t. So it's the in minus the out. So we're going to have this as our differential equation. Now, before we get into solving the differential equation, while we have this in mind, we want to know when the tank is half empty. That's when the volume is 5 liters. But since we have this equation that gives us the volume, we can quickly determine what time that should be. 5 equals our 10 minus t. That will take place in 5 minutes. So once we get our equation x of t, we just need to plug in 5 and we'll get our answer. So this is what we're looking for. X of 5 is what? So that's our goal. Now let's look at solving this differential equation. So here are independent variables t, our dependent variables x. So let's move the things that involve our x term to the other side. So we'll add this term over to both sides and we get our dx dt plus our 3 over 10 minus t times x equals 40t. Now we think through our different solution strategies for solving differential equations, and one thing that we might notice is that this is a first order linear differential equation, so we know we can use our integrating factor method. Now we know our integrating factor is e raised to the integral of what's getting multiplied here by our x, so we have the integral of 3 of 1 times 10 minus t dt. Now, I would recommend that at this point you pause the video and work the problem out on your own. And then you can unpause it to see the solution worked out step by step, or if you're confident in your answer, fast forward to the end and check your work. See if we agree. If we don't, go back through the video and kind of check piece at a time. So use this moment to work on the problem yourself, and then if need be, you can see the step-by-step solution when you unpause the video. So our integrating factor will be e to the negative 3 natural log absolute value of 10 minus t whenever we integrate this. Now, in order to have e raised to the natural log of something and use the inverse properties of the e and natural log since they're inverse functions, I need to have my constant multiple. Constant multiples of natural log come up as exponents, so this becomes to the negative 3. And we have e raised to the natural log of 10 minus t to the negative 3. That would give us 10 minus t to the negative 3 power. Now I'm going to multiply all sides by that integration factor, and we'll get... Now we recognize that the left-hand side is the result of product rule for derivatives. For the original product of this multiplied by this. So when we integrate both sides with respect to t, we know the left side simplifies back to the original product. And now we need to consider how are we going to integrate this expression with respect to t. First thing we do is let's rewrite this. I'm going to bring the 40 out in front as a constant multiple. And here, as we want to integrate this, I think we'll find u substitution to be quite helpful, because our numerator and denominator are relatively closely related. If we let u be 10 minus t, then we can rearrange this to solve for t, and we get that t is 10 minus u. And what this is going to allow us to do is it's going to allow our denominator, which has the exponent, to become quite a bit simpler. Our numerator becomes a difference, but then if we have just a single term in the denominator of multiple terms in the numerator, we can split that up into two separate integrals. Now in order to do this, we need to find our du. Our du is negative dt. We have our positive dt, so we're looking at a negative du is our dt. Substitute this into our integral, and we get negative 40. I'm distributing the negative here to the constant multiple. of 10 minus u over u cubed du. And now we see that I can divide each term and then take the difference, and that will split me into two separate intervals. So we have negative 40 all times the integral of 10 over u cubed du minus the integral u divided by u cubed is 1 over u squared du. Both of these are nice integrals that we can solve. So this is u to the negative 3. We add 1 to the power. That gets us to u to the negative 2. We need to divide by that. So we have 10 over negative 2 times u to the negative 2 minus, this is u to the negative 2. Add 1 to that, we'll get u to the negative 1. Divide by that. 1 over negative 1 times u to the negative 1. And then plus our constant of integration. All of this was equal to our 10t to the negative 3 times x. And then we need to recall u was 10 minus t. Now we know that our undetermined constant is not really affected by this negative 40. We can still call it c. Negative 40 times undetermined constant is still undetermined constant. I've substituted back for u as 10 minus t. And then we're almost to the point where we can solve for x. We just need to simplify the left side. We're going to divide both sides by this expression. So it divides through on the right side as well. Negative 40 times negative 5 is positive 200. 10 minus t to the negative 2 divided by this becomes t to the 10 minus t to the positive 1 power, plus, or I should say minus 40 when we distribute. This divided by this would give us a 10 minus t squared. Now we have this divided by this, and we will get plus c times 10 minus t to the negative 3. Or sorry, positive 3. Whenever we divide by the negative 3, that becomes a positive 3 exponent. So we're almost at our goal. We know our goal was to find the amount when the tank was half full. Based on our understanding of how the volume changes with respect to time, we found that it takes 5 minutes to pass for the tank to reach half capacity. So we want to find what's the amount after 5 minutes, but we can't do that until we know the value for this constant of integration. So in order to find the value for the constant of integration, let's go back and think about what was happening about the amount of this solute, or I guess in this particular example it was some pollutant, at time t equals 0. So at time t equals 0, we had, if we go back to our problem, 10 liters of clean water. That means for our t, comma, our amount of t, when time was 0, before we started adding in the pollutant, the amount was 0. So let's use this to solve, to figure out what our constant of integration c should be to make this initial value work. So we know 0, 0 is our initial value. The amount is 0 when time is 0. $200 times 10 gives us 2,000 minus 40 times 100, because our 10 is squared, gives us 4,000. And then 10 cubed gives us 1,000. So we have the equation 0 equals negative 2,000 plus 1,000 c. So when we solve this, we're going to add the 2,000 over, divide by 1,000, we get C needs to be equal to 2. We're going to plug that back into our original equation, and then we can evaluate the amount of pollutants remaining in the tank at 5 minutes. We're going to place our amount C with 2, and then we calculate the amount after 5 minutes. Whenever we calculate this, we get that the amount after 5 minutes ends up being 250 grams. Because we were measuring the amount of pollutants that were coming in, the concentration was in grams per minute, or grams per liter as the concentration. So that's an example of one of our mixing problems. As we finish up, I just want to draw our attention back to this general rule that we'll use for these problems, that we can find the rate of change as it is going to be the rate in times the pollutant concentration coming in minus the rate out times the pollutant concentration that's coming out, which can be measured by our x of t, which gives us the amount in the tank at time t, divided by the volume in the tank at time t. So if you use this basic rubric and then use our different solution strategies for solving the resulting differential equation, you'll be able to find x of t, which gives you the amount of the solute or pollution in the tank at time t.